Quality education is a human right.
Hi guys, in this video, we're going to feature a question from the Q&A. For the purpose of this video, I'm going to assume that you know how to find the absolute and local maxes and mins. I'm also going to assume that you have a basic introduction to optimization. Now let's get started with this question. In this slide, we will preview the basics to optimization. Now, optimization is used for real-life examples when we want to find the absolute max and min. For example, if we want to maximize profits or if we want to minimize resources. Now, the steps for optimization would start with drawing a diagram. We draw a diagram so that we can visualize our example and what we need to find. The second step after that would be to label the diagram with variables. Sometimes the problems come with variables, like in today's example. The next step following that would be to express the value you want to optimize as an equation. Now, the equations could be area or perimeter or volume. The step after that is to express the equations you want to optimize with only one variable. In the example with area equals to length times width. So we'd want to only use one. So we'd have to use only length or only width. The step after that is to find the constraints of x. We want to find the lowest point x can be and the highest point that x could be. After that, we could find the absolute minimum or the absolute maximum of x. Now, in case that we cannot find the constraints, what we need to do is that we need to find the local mins or max. So now that we know the steps to optimization, the next slide we will begin solving. So now on this slide, we have our question, and you could take a moment to pause the video and read the question for yourselves. Now that you're back, we can now start to familiarize ourselves with the question. So we start by drawing the diagram for this. So here we have that it's an upside down cone inside a larger one. So we could first start by drawing the upside down cone. So now that we have our smaller cone, we know that it's inside a larger cone with the vertex being right here, being at the middle of the base of the larger cone. So with that information, we can draw the larger cone. So now we have it so that the vertex of the smaller one is at the middle of the base of the larger cone. If we also look here, we could notice that the base of the larger cone is parallel to the base of the smaller cone. That's also part of the question. So now we have a visual representation of our question. So in the next slide, we will label this diagram with variables. So on this slide, we will label the variables for this diagram using the hint. So we could begin by looking at big H and big R should be the height and the radius of the large cone. So we begin labeling the height and the radius. So thanks to the hint, we could see that this one would be H and this line would be big R. So that we continue, and small h and small r should be the height and the radius of the small cone. So now that we know that, we can label that as well. So now we also label the variables. We have small h and small r here. Now, the challenging part of this question will be the last part of our hint. We have to use similar triangles to get the equation we want. So now for this, we'd have to find the cross section to turn a three-dimensional shape into a two-dimensional shape. So if we look here, this would be the two-dimensional triangle that will come out. So now we have to prove that triangles in this one are similar. But if we take a look here, the red triangle, we cannot prove that that's similar to the blue triangle. So what we have to do is find another triangle so that we could substitute that so that it's similar to the blue triangle. So if we have a look here, we have that this triangle right here. We could say that this triangle is similar to the blue triangle. This is because if we look here, this is a 90-degree angle for the blue triangle. And here in the green triangle, we also have a 90-degree angle. Now we look at this cornered variable and they literally have the same angle. So we could put that this one, they're both the same. So now that we have those two angles, since they both need to add up to 180 degrees, we can also say that this final angle and this final angle we can say that they're similar. So using the AAA rule, we just proved that the green triangle and the blue triangle are similar, but not congruent. So now that we have that they're similar, we can begin labeling them. So if we look here, this line is still R, big R. This whole side would be H. This side, the red line, would be little h. And this side would be little r. So we can now set up proportion, which in our case be big R over big H. That's equal to, so we have R here. We already have that. But this side is still unknown. So to get this side, what we need to do is that we'd have to subtract the big H minus the small h. The big H minus the small h would be this leftover part that we need. So now we've also labeled this unknown side. So now that we have that, we plug it into our equation. So we have big R over big H is proportional to the little r over big H minus small h. So in the next slide, we'll find an equation for the value that we're trying to optimize. So now that we've labeled our variables, we want to find what value we are trying to optimize. If we look at the question, we have that it says we want the largest possible volume for the smaller cone. So what this means is that we are trying to maximize the volume of the smaller cone. Now, if you remember, the volume for cones 1/3 pi r squared times height. Now, the problem with this volume equation is that there's two variables. The two variables that we know that are here are r and h. We know that r and h are variables because when we're adjusting the volume to find the largest possible volume that there is, we're also switching the radius and the height. So in the next slide, we will be adjusting the volume equation so that there's only one variable. Now that we have our volume, what we want to do is that we want to find it with only one variable. Now, if you remember, the two variables are little r and little h. So we're going to have to find out one of them, which in our case, we were going to find little r by using the proportion that we found before, which is at the bottom right here. So we can begin by isolating little r. We have little r is equal to, and in order to isolate, we multiply big H minus small h to both sides. So what we end up having is big R over big H, and that's being multiplied by big H minus little h. Now we distribute so that we end up having big R minus big R times little h divided by big H. So now, if you look at this, you might be thinking that we only just added more variables. We have the big R, the big H, and the little h. But if we think about the question, the big R and the big H, they represent the height and the radius of the large cone. Now, the large cone isn't being changed, only the smaller cone that's being altered so that we can find the largest possible volume. So therefore, the big R and the big H, they remain constants. So we could treat them like constants. So now we could plug in our little r into the volume equation. So we have that as equal to 1/3 pi, and then we multiply what we found for little r. So we bring it over. And then we mustn't forget that the little r is being squared, so we must also square what we brought over, and we multiply little h. Now, in order to simplify this part, what we have to do is we have to FOIL, which we could see right here. We're foiling these two. So that's going to be our next step. So we have that it equals to 1/3 pi. And then we open our parentheses for what we're going to FOIL. So then we have big R being multiplied by big R. So we have big R squared. Now for the next one, we have that we're multiplying big R times negative big R times H divided by big H. Now if we notice here, we're going to be doing that twice. One for these two and one for these two. So since we're doing that twice, we could save time by putting the two and then just solving the first one and putting that here. So big R times small h, that'd be So this is what we get for the second one. Now our final one is these two. So we could multiply. So it's big R times big R. That's big R squared. And then we have little h times little h. So we have little h squared. And then we have big H times big H in the denominator. So in the denominator, we have big H squared. So we finished foiling, so we could close our parentheses. And don't forget the little h that is still being multiplied. Now, for the next step, what we want to do is that if we notice here, all three of these have big R squared. So what we're going to do is that we're going to factor them out, and we're going to distribute the little h into these three. So once we factor out R squared, what we get outside the parentheses is R squared being divided by 3 times pi. And then inside, we're going to have to distribute the h. So for the first one, we have big R squared, but we factor that out, so it would be 1. And then we multiply by the small h, so we have little h. And then for the next one, we have another R squared, so we factor that out, and then we multiply the little h. So we end up having 2 times the little h squared, because there was already a little h here, divided by big H. Now for the last one, again, big R squared factored out. So we have h squared, little h squared times little h. So it's little h cubed, and that's being divided by big H squared. We close the parentheses again. So now that we've simplified this, for the next slide, we will be finding the constraints, which is the smallest possible value for the little h and the highest possible value for the little h. The next step of our process is to find the constraints of the little h. So in order to start this, we have that h exists within, and now we have to think of the smallest possible value that h could be, little h could be. So if we think about it conceptually, little h, the smallest it could be is 0. It's because the height of a cone cannot be negative. So the smallest it could possibly be, we have is 0. So now we have to think about what's the largest possible value the little h could be. Now, if we think about it conceptually again, the little h represents the height of the smaller cone. So it's inside the larger cone. So the largest it could be is the same height as the larger cone, which is big H. The reason it can't be greater than that is because the small height would surpass the larger cone, which would no longer be inside. So it'd go against what the question told us. So with that reasoning, we can have that big H is the largest value that it could be. And then we found our constraints. So now with this information, we can finally use calculus to find the absolute maximum value for the volume of the smaller cone. So now that we have the equation with only one variable and our constraints, we can now begin to find the absolute maximum. The first part is finding the critical points. In order to do that, we have to find the derivative of v of h. So if we notice here, 1/3 pi times big R squared, those are all constants. So when we're deriving, we could simply keep them at front and temporarily ignore them. So now we can begin deriving inside the parentheses that we have here. So for the little h, it would just be 1. For this one, we bring down the 2 and we multiply it by the 2 that's already there. So we have 4 little h, and then that's being divided by big H. And again, the big H is being left as a constant because we already found that out before. So then we add, and then we derive the next one. We bring down the 3, so it's 3 little h squared. It's being divided by big H squared. So now that we derived that, to find the critical points, we set it equal to 0, and we have to isolate the little h. So now that we have this, what we have to do is that we have to divide the constants that we first ignored in the beginning to the other side. The reason is because they'll get canceled out and we'll be left with a much simpler equation to simplify. So if we move these constants to the other side, we have 1 minus 4h, 4 little h divided by big H, plus 3 little h squared divided by big H squared. And again, it's equal to 0. So now that we're at that point, in order to simplify further, we must notice that this equation is the same format as the standard form equation for a parabola. So if we notice that, what we have to use is the quadratic formula to find what little h is equal to. So in order to first start with the quadratic formula, we must first remember that we need a, b, and c. They're written at the top corner. So if we look at our equation, our a will be the one next to the variable squared. So we have 3 divided by big H squared. That would be our a. Now for our b, it would be negative 4 over big H. And if we look at our c, it's simply 1. So now that we have all 3, we could start finding the quadratic formula. So the first part, we have negative b, which in our situation, 4 over big H. And we have plus or minus, and then we add in our square root, which would first part would be b squared, which is negative 4 over big H times negative 4 over big H, which is 16 over big H squared. And then we subtract 4ac. So we multiply 4 times a, which is 3 over big H squared. So it's 12 over big H squared. And then times c, which is 1. So that's simply 12 divided by big H squared. So we finished our radical. And now we need our denominator for the quadratic formula. It's 2a. So in our situation, 2 times a would be 6 divided by big H squared. So we begin by first simplifying our square root. If we notice here, these two both have the same denominator, which is big H squared. So we could just subtract the numerators. So we have the square root of 4 divided by big H squared. So now that we have that, if we notice here, we're lucky enough to get a square root that could be easily simplified. The square root of this would be 2 over H. The reason it's that because if we multiply 2 over big H times 2 over big H, we get 4 over big H squared, which happens to be what we had here. So now that we found that, we bring it over. So we have 4 divided by big H plus or minus 2 over big H, and then divided by 6 over big H squared. So now we simplified, and now we can begin finding our different small h values. So since this is plus or minus, we have to find when it's adding and when it's subtracting. So for this one, for the first one, we'll have the one where it's adding, and then the next one would be when we're subtracting h. So we start with the first one where we're adding. So we have 4 over h plus 2 over h. That would be 6 over h. So we'd have 6 over h, and then we're dividing 6 over big H squared. So dividing, we actually multiply the reciprocal. So we'd end up having multiplying big H squared over 6. So if we multiply these two, 1h cancels out, and then the 6 cancels out. So what we end up having is h. So we found our first little h value. So now we have to solve for when we're subtracting. So we have 4 over big H minus 2 over big H, which ends up being 2 over big H. And again, we multiply the reciprocal, and it's the same denominator, so we write the same format. when we do this, the end result we end up having is big H over 3. So now we have our little h values for the critical points. Now please give me a second so I could clear the space. So now that we have our critical points, the final step is to plug it in to V of H. So we have V of big H, and we'll first solve for that one. So if we see here, the 1/3 pi big R squared remains the same. Now, inside the parentheses, that's when we begin plugging in the big H. So the little h becomes big H, and we subtract. So we have 2 times big H squared divided by big H, and then we add big H cubed divided by big H squared. So now that we have this, we can begin to simplify. So if we notice here, the H squared and the H, one H cancels out. So inside the parentheses, we have the big H remains the same. But now we have 2 times big H. And then we add H cubed divided, big H cubed divided by big H squared. Now, if we notice again, we could simplify by subtracting 2 in the exponents for both of them. So we have big H. Now we bring what we had up on top down of 1/3 pi R squared, and then inside the parentheses, big H minus 2 big H is negative big H, and negative big H plus big H end up having 0. So 0 multiplied by anything, we already know that V of big H is equal to 0. So now we found one critical point. Now we have to do the same, but for big H divided by 3. So we follow the same procedure, and we have 1/3 pi R squared and then inside the parentheses, we begin substituting in. So we first start with big H over 3 now. We subtract 2 times big H over 3 squared. And then that is being divided by big H. And then we add, and then now we have big H over 3 cubed divided by big H squared. And we close our parentheses. So now we begin simplifying. Inside the parentheses, the big H over 3 stays the same. Now for big H over 3 squared, that would be big H squared over 9, and then we multiply that by 2, so we have 2 big H squared and we're dividing 9h. So now move on to the next one. Big H over 3 cubed. That would be big H cubed divided by, now the 3 cubed, since it's dividing, that would be in the denominator now. So it'd be 27 big H squared. So now that we have that, what we do next is that we put them as similar denominators so that we can simplify inside. So we set all of them equal to the denominator being 27, and we simplify the h's. For the first one, it only has one h, so that one's fine. And then for the next one, we cancel out one h because there's one in the denominator and 2 in the numerator. So we end up 2 big H divided by 9. And then for the last one, it's big H cubed in the numerator and big H squared in the denominator. So we end up just having big H over 27. Now we switch the denominators so that they end up simplifying. So the best number to choose would be switching them all to 27. So this being multiplied by 9, this being multiplied by 3, and this one stays the same. So we bring down the 1/3 by big R squared. And then in the parentheses, it's 9 big H over 27 minus 6 big H over 27 plus H over 27. Inside the parentheses, 9 minus 6, that would be 3, and then plus the H, that would be 4. So it'd be 4H plus 27 being multiplied by the constants we left outside. Now our final solution for this one, we'd have this would be our final solution for V of big H over 3. Now that we found the critical points, we can't forget to include the end points. Now, if you remember from before, we had that little h, it includes 0 and big H. For this one, we don't need to find big H because if we look, the critical point was already an endpoint. So thankfully, we already know this one. So now what's left is V of 0. So if we plug it in, 0 is being subtracted from 0 because it's 0 squared and then multiply plus 0 cubed. And then inside the parentheses, So the constants are left outside. And as we discussed, all that's left is inside is a 0. So when we multiply again, we have 0. So the three values that we should compare is v of 0, v of big H, and v of big H divided by 3. So if we look here, the biggest one, where absolute maximum, would be v of big H over 3. So now, in most cases, we would be done with just having this. But if we remember our question, there's another part that we need to solve. In the next slide, we will finally finish this entire question. So the final part to our question is asking to find the fraction of the volume that the small cone occupies. In order to find that, we need to set up a ratio. The ratio that we could set up is the volume of the small one being divided by the volume of the big one. Now, thankfully, through all the work that we found, we already know the volume of the small cone. It's the red one to this side right here. And we also know the volume of the big one. It would be the standard volume for a cone. So knowing that, we could find our answer. So we begin by plugging in the values that we know. And in the denominator, we also know it. So we could also plug that in. So if we take a look here, thankfully, most of the things here cancel out. The H, the big H and the big H cancel out. The big R squared, they cancel out as well. The pi's, they also cancel out. So what we're left with is two numerical values being divided by each other. So we set up 4 over 81. And remember, we multiplied the reciprocal when we're dividing. So that's being multiplied by 3 over 1. Now the 3 and the 81, they cancel out. From the 3, it becomes a 1. And from the 81, it becomes a 27. So we're left with 4 over 27. The smaller cone takes up 4 over 27 of the space that the volume of the larger cone. That's it for today's example. If you want an introduction to optimization, leave a comment down below. And if there's any other question, you could also leave it down below. Thank you for watching.
If you have any questions or any practice problems you would like to understand better, please comment them down below. During our bi-weekly Q&A, we will tackle these problems from the comment section.
Please like and subscribe so that our videos can reach more calculus students. See you next time, you sleuths.